This video is about partial orderings, which are relations that instead of focusing on equality, focus instead on inequality and hierarchy. A relation R on a set S is a partial ordering if it satisfies all three of the following properties. So first, we want it to have the reflexive property. So that is, for any A in our set, we want A to be related to itself. So that's very similar to what we require for an equivalence relation. We also want transitivity to be in place. That is, if we have three objects in our set S, A, B, and C, and if A is related to B, and in turn B is related to C, then we expect A to be related to C. So again, this is a property that's shared in common with equivalence relations. Now we break with equivalence relations when we come to this third property, which is called anti-symmetry. So for any A and B and S, if A is related to B and also B is related to A, then the only way that can happen is if A and B were the same thing to begin with. So this is very different from the situation with equivalence relations, where whenever A is related to B, we expect B to be related to A. So for equivalence relations, we took our motivation from ordinary equality of numbers. Right? Ordinary equality satisfies all of these properties of equivalence relations. For partial ordering, it's good to think about inequalities like less than or equal. Okay, those should be the things that we have in mind that have all the properties of a partial order. You know, for instance, any number is less than or equal to itself. And if A is less than or equal to B, and B is less than or equal to C, then that implies that A is less than or equal to C. So that gives us reflexivity and transitivity. But now, if you have A being less than or equal to B, and you have B being less than or equal to A, then the only way that can happen is if A is equal to B. So that's the anti-symmetry property. So anyway, the main thing to keep in mind if you're looking for an example of a partial order is to look at the inequality relation. Okay, as we were saying just a moment ago, if you take any set of numbers, the inequality relation defines a partial ordering. Another example is if you let S be any set and you look at the power set of S. So remember, the power set is the set of all subsets of S. Then the subset relation defines a partial ordering on the power set. And then finally, the divides relation defines a partial ordering on the set of natural numbers. At the beginning of these slides, we talked about how a partial ordering determines a hierarchy of elements in a set. And we can have a graphical depiction of that hierarchy using something called a Hasse diagram. So if we've got a set and a partial ordering on that set, what we can do is form a node or a label for each element of the set, along with lines connecting related nodes. So we don't want to connect every pair of related nodes with lines, though. We only connect immediate successors. That is, we only connect X and Y if Y is sort of the smallest thing that is sort of bigger than or equal to X. So if there's any intermediate object like Z, then we do not connect X and Y with an edge. So the sort of smaller elements go at the bottom of a Hasse diagram, and as we move upward, the objects become larger. So here we see an example of a Hasa diagram for the power set of the set 1, 2, 3 with the subset relation. Okay, so what is the power set of the set 1, 2, 3? Well, it's this set 1, 2, 3 and all of its subsets, including the empty set. Now, the smallest set in this entire hierarchy is the empty set. It's a subset of everything, right? Now, what are the immediate successors of the empty set? That is, what are the smallest sets that the empty set is a subset of? Well, you have the singletons, 1, 2, and 3. So we draw ascending lines from the empty set to 1, to 2, and to 3. So now we're up at this level here. And now we ask ourselves, what are the immediate successors of the sets 1, 2, and 3? Well, the immediate successors will be these sets that have 2 numbers in them. So both 1 and 2 are subsets of the set 1, 2. Both 2 and 3 are subsets of the set 2, 3. And 1 and 3 are subsets of the set consisting of 1 and 3. Okay, now what is the immediate successor of all 3 of these sets with 2 elements? Well, all 3 of those have a common immediate successor, and that is the entire set 1, 2, 3. So there is the Hasa diagram. So here we see the Hasa diagram for the set 2, 3, 4, 6, 8 with the division relation. So we ask ourselves, well, what are the smallest things in our Hasa diagram? Well, the numbers 2 and 3 are those smallest things. And now we ask ourselves, well, what are the immediate successors of 2 and 3? So that is, what are sort of the smallest things into which 2 and 3 divide evenly? So 2 divides evenly into 4 and to 6. So we draw these ascending lines from 2 to 4 and to 6. 3, its immediate successor is 6. That is, 6 is the smallest number in the list that is divisible evenly by 3. So we have an ascending line from 3 to 6. Now, we've drawn, we're now up at this level, including 4 and 6. Are there any immediate successors of 4? Well, we see that 8 is divisible by 4, and there's no smaller number in between that's divisible by 4, so we draw an ascending line from 4 to 8. 6 does not have a successor. Okay, now at the bottom you see this list of so-called minimal elements and maximal elements. So minimal elements are any elements that occur at the bottom of the Hasa diagram. Okay, so they are ones where there's no downward edge emanating from them. Now, maximal elements are the ones that are more or less at the top of the Hasa diagram. So those are the ones where there's no upward edge emanating from them. So in this case, 6 and 8 are the maximal elements. One thing we like to do sometimes is to take a partial ordering on a set and force a total order. In other words, we have a hierarchy with maybe multiple minimal objects and multiple maximal objects. And what we want to do is sort of list those objects in some kind of reasonable order from beginning to end. So the way that we do that is by making use of a Hasa diagram. So to form what's called this topological sort, that is putting the elements into some sort of reasonable order, we just choose any minimal element in our Hasa diagram, and we add this element to the end of the list we're making. and then remove that element from our Hassa diagram, and then we repeat step 1 and then step 2 again and again until we're out of elements. Okay, one application of a topological sort is deciding an order in which to take certain classes when there's a hierarchy on these classes determined by prerequisites. Like, for instance, we see here that Calc 2 has Calc 1 as a prerequisite. So we're going to do a topological sort. So that means we're going to put these classes in some kind of reasonable order where you could, take the first class, then take the second, then take the third, then the fourth, and so on and so forth, without violating the hierarchy that's given in this Hassa diagram. Okay, so the strategy on the previous slide suggested that we start with a minimal element. So Calc 1 is the only minimal element, and so we must start with it. And then what do? Well, the strategy tells us to remove then Calc 1 and any ascending edges from Calc 1 from the Hassa diagram, and what's left is a new Hassa diagram where we have two minimal elements, namely Calc 2 and Programming 2. So either one of those could go next in our list. We've decided to put Calc 2 next in our list, so we remove Calc 2 and any ascending edges. And now we have a new Hassa diagram with three minimal elements, namely linear algebra, Calc 3, and Programming 2. So we've decided to go with Calc 3 next. So we remove it and any ascending nodes. We look at the remaining Hassa diagram. We pick a minimal element like Programming 2. We remove it and any ascending edges. And now we again see that, well, what are our minimal elements now? Well, we have software development, which is a minimal element. We have linear algebra, which is a minimal element. So we're going to do software development next. We remove it and any ascending edges. And then we have linear algebra. We remove it and any ascending edges. And then the only thing that's left over is the 3D computer graphics, and so that goes at the end of our list. Some partially ordered sets, even though they look superficially different, are fundamentally and structurally the same partially ordered set. So how does that happen? So let's suppose we have two partially ordered sets, x1 and x2. We say that these two partially ordered sets are isomorphic, meaning the same, if there's a one-to-one correspondence from x1 to x2. That is order preserving. That is, that if A is less than or equal to B in x1, then f of A is less than or equal to f of B over in x2. So if we have this situation, we say that this function f is an isomorphism. And we use this notation to indicate that the two partially ordered sets are isomorphic. One way you can tell that two partially ordered sets are isomorphic is by looking at their Hassa diagrams. So if the Hassa diagrams are identical, then the partially ordered sets must be isomorphic. So here what we're doing is we're looking at the Hassa diagram for this set under the divisibility relation. So here the smallest element is 1, and its immediate successors, it divides evenly into 2, 3, and 5. They in turn divide evenly into 6 and 15 and 10, and then at the top of the hierarchy is 30. Now this figure should look familiar to you because we've seen it before in this video. In fact, when we looked at the power set on the set 1, 2, 3 under the subset relation, we got a Hasse diagram that looks exactly like this. So let me remind you that at the bottom we had the empty set. We had the singleton 1 here. We had the singleton 2 here. And the singleton 3. And then 1 and 2 both sit in the 2-element set 1, 2. 2 and 3 both sit in the 2-element set 2, 3. And 1 and 3 sit in the 2-element set 1, 3. And then all 3 of these 2-element sets sit in the largest set 1, 2, 3. So our isomorphism here, F, would take, for instance, the set 1, 2 in this post set and send it to 6 in this post set. Finally, we'd like to talk about the ideas of meet and join. So we start with a partially ordered set. And if we take elements A and B in that set, the meet of A and B, denoted like this, is essentially the greatest lower bound of A and B. So what that means is that this meet is less than or equal to both A and to B. And it's special in that if you have any other element X that is also less than or equal to A and less than or equal to B, then X must be less than or equal to this meet. Okay, there's a similar object called a join of 2 elements of X. And this is essentially a least upper bound. So the join will be an object that's bigger than or equal to A and bigger than or equal to B. And further, if there's some other object X that's also bigger than or equal to A and bigger than or equal to B, then it must also be bigger than or equal to the join. Here we compute some meets and joins. Again, our partially ordered set consists of the numbers 1, 2, 3, 5, 6, 10, 15, and 30 with the divisibility relation. So we first compute the meet of 3 and 2. Now what is this again? So we're looking for the largest object in our hierarchy that is less than both 3 and 2. And we see that that should be 1. Okay, now what about the join of 3 and 2? So the join is going to now be the smallest object in our hierarchy that is larger than both 3 and 2. So 30 is larger than both 3 and 2, but it's not the smallest thing in our hierarchy that's larger than both 3 and 2. That is actually 6. Okay, now let's move on and compute the join of 15 and 10. So once again, we're looking for the smallest object in our hierarchy that is larger than both 15 and 10, and that is 30. And then finally, we have the meet. So this is a join. And finally, we have the meet of 15 and 2. So we are looking for the largest object that is smaller than both 2 and 15 in our hierarchy, and 1, again, is the answer to that.